if the spectrum is continuous, the summations that we wrote in previous videos will become integrals. So for example, if we consider the inner product between two states of the kind x and x prime, and these states are orthonormal, well, in the previous videos we wrote something like delta x x prime or x prime x, it's symmetric, where this is the Kronecker delta. But if x prime and x are continuous, meaning that these states are, that they can be infinitesimally close to each other and they are uncountable. So instead of writing a sum of the kind summation over x, then we have c sub x x, well, x should be considered as a continuous variable. So instead of writing a summation, we have an integral, even though the principle is the same. And the Kronecker delta becomes a Dirac delta of the kind x minus x prime. Now, for the sake of convenience, let's think that we have a one-dimensional space. So we are in one dimension, and if we are, for example, in a three-dimensional space, instead of having a Dirac delta of this kind, we have a three-dimensional Dirac delta. So this would become a vector, and if that's a vector, we have something like delta of x1 minus x1 prime, delta of x2 minus x2 prime, dot dot dot. So you multiply the Dirac deltas. That's an n-dimensional or a d-dimensional Dirac delta. But we still have a completeness formula also in here, for example. So we can also rewrite this expression as, for example, as x prime, or if you want to use the variable r, we can also use r instead of x, but you get the idea. So we might have something like this, x prime, r, and then we have x, and here we integrate over r, over the variable r, over all the possible values of r. So this is still a completeness formula, but instead of summing over r in a discrete manner, we integrate over r, right? And of course we still get delta of x minus x prime, because the integral over r of r is equal to an identity operator. And since r is still part of this basis, this inner product would be equal to the Dirac delta of x prime minus r, whereas this one is the Dirac delta of r minus x. And due to the properties of the Dirac delta, one can easily check that this equality here holds, and that's quite simple to see. For example, we can use the property delta of r minus x multiplied by some function f of x. This can be written as delta of r minus x times f of r, because we can evaluate the function that multiplies the Dirac delta at the point where the Dirac delta has its peak. So we can easily make sure that by using this property, that one is also satisfied. It's quite easy to see. But this is the position space. It's the so-called position space. And by the way, these functions here cannot easily be normalized, cannot be normalized actually, because if you consider x prime equal to x, you can see that we get a Dirac delta of 0, which is an infinite amount. It's an infinite number. So in principle, these functions are not normalized, but they are orthogonal, because if x prime is not equal to x, the Dirac delta gives you 0. And we can try to consider another space where instead of considering the position variable, we have momentum. So we have the states of the kind p, and p should be considered as a continuous variable as well. And we still assume that, for example, we have p prime p equal to the Dirac delta of p minus p prime. So the property is the same, meaning that these states are orthogonal. They cannot be normalized, as I said earlier, but they are orthogonal, because if p is not equal to p prime, we get 0. And we still want to consider a completeness formula also in this space. and something similar holds, something similar to this one holds, but I want to consider another formula where we mix position and momentum. And in particular, if we start from, let's say, x prime inner product x, we know that this is equal to delta of x prime minus x. But now I want to use the completeness formula in momentum space, and in particular I want to write something like this: integral dp of the exterior product, or if you want the tensor product, or if you want ket times bra, equal to an identity. So I'm going to use this expression there, and if I do that, I have something like this. I have an inner product between x prime and p, then inner product between p and x, and then we have to integrate over p, and this should be still equal to delta of x minus x prime. Now, in momentum space, there is an important function that gives rise to a Dirac delta, and in particular we have a function that also contains the variable p. It must contain the variable p, and another property that we would like to preserve is the fact that, for example, if we take the mod squared of such an inner product, we should get 1, and similarly, if we take the mod squared of such a product, we should get 1. I mean, if we calculate such an inner product, we are able to calculate such an inner product as well. We simply have to change x prime to x, and since p inner product x is equal to xp star, well, we have a relation between these two. We change x prime to x, and then we have to take the complex conjugate. And of course, if this is normalized to 1, this one here should also be normalized to 1. It's quite intuitive. But now, if we impose such a constraint, it means that x prime p should be proportional to a complex exponential. And the complex exponential here should contain a function of p and x prime, because here we have x prime. It is quite easy to see that this function should be linear in p and x prime, because we have an important integral that occurs very often when we have to deal with Fourier transforms, for example. We have an integral of the kind integral dp, and we have to integrate from minus infinity to plus infinity. I'm not going to write the limits of integration. E to the I p times x, remember that we are in a one-dimensional space for convenience, but this can be easily generalized to a general number of dimensions. P dot x, and we should divide by h bar, because remember that h bar has the same units as p times x, and we need to get a dimensionless quantity. And if we divide here by h bar, we should divide here by h bar as well, because it's as if we integrate over p over h bar. And if we take x minus x prime instead of x, this result, the result of this integration gives rise to 2 pi, and if we want, we can get rid of the factor of 2 pi by putting it here, so we put 2 pi, and then we get delta of x minus x prime, which is exactly the result that we have there. And considering this constraint as well, we can easily see that, for example, we can take the inner product between x prime and p as, by the way, this result holds both for a plus and also for a minus. So if we put a minus there, we still get the same result. It's a real quantity, and we get this distribution. We can call it distribution or generalized function. Sometimes to be brief and to try to simplify our way of speaking, we can say that this is a function, the Dirac delta function. but you get the idea. And we can see from here that this inner product should be proportional to E plus or minus, and let's choose a minus, but with this minus x prime becomes a plus, so we get I p x prime divided by h bar, and then we should take the square root of this, so we divide by the square root of 2 pi h bar. And similarly, of course, we get that the inner product between p and x is equal to the complex conjugate of this, so we get e to the minus I p x divided by h bar divided by the square root of 2 pi h bar, like this. So it's quite easy to see. And in n dimensions, instead of having the square root here, this should be raised to the power n, for example, if we have n dimensions, and we should reinterpret this product as a dot product. So we would have something like p dot x as vectors. And as I said, here you have to raise this to the power n, the number of dimensions. Or if you want, 2 pi h bar to the power number of dimensions divided by 2. This factor of 2 comes from the square root, of course. Simple as that. Now, before concluding this video, I would like to consider the expansion of the state psi. Remember that this depends on t, and we want to expand it in the momentum space. So in this case, since we are considering a continuous variable p, we have to integrate. We don't have to sum. We don't have a discrete sum, but we have to integrate. And here, the coefficient of the expansion, of course, will be a continuous function of p, and it will also depend on t. Then here I will put the ket p, and if we are, let's assume that we are in 3 dimensions now, so we have the vector p, so we have to integrate over d3p, like this. So in this case, instead of having n, we will have 3 when we consider 3 dimensions. So we can take this as a definition. We have the coefficients of the expansions, and we have the vectors of the expansion that should, of course, be p, because these are the vectors of our bases. And we can write, for example, phi of pt as the inner product between p and psi of t. Remember that these are orthogonal, so they are not normalized, because their inner product between p and p prime is equal to the Dirac delta. In this case, this should be interpreted as a 3-dimensional Dirac delta, and when p is equal to p prime, we get an infinity there. Now let me cancel this because I don't want to clutter my whiteboard too much. But now I want to use a completeness formula, in particular a completeness formula in the position space. So we are going to integrate over R. Let's write it like this, d3r. And then we have the vector p, the vector r, and then we have the vector r written. So first we write it as a ket, then we write a bra, so it's like a tensor product, psi of t. I've already written d3r here, so I don't have to write it here. And this can also be written in the following fashion. In particular, we already know how to write the inner product between p and r. That inner product is simply equal to e to the minus I over h bar. And then here we have p, the vector p is a 3-dimensional vector p dot r divided by 2 pi h bar to the power 3/2. And then here, this inner product between the position vector r, if you want, and the ket psi of t, it's quite easy to understand, also considering what we said in the previous videos, that this is just the wave function of rt. So we can write this as the wave function psi of rt. You can check the considerations that we made in the previous videos. But what is this expression here? If we check the expression, we can see that basically we get some kind of Fourier transform of the wave function in the position domain. We transform it to the wave function in the momentum domain. So we go to the momentum domain. And of course, you can easily understand that if we want to... So we could also write this function in terms of this one by taking the inverse Fourier transform of this. It's quite intuitive. Or you can also derive it in the following manner. So we can write psi of RT, which by definition is equal to inner product of R psi of t, but we can use the completeness formula in the momentum space. So we integrate over d3p, then we have inner product between R and P, inner product between P and psi of t. Sorry about my handwriting here. And this expression is simply given by what we call the phi of PT, whereas in here, this inner product, we have already calculated it. It's basically the complex conjugate of that. So we get e to the I over h bar, so we get a plus instead of a minus, then p dot r divided by 2 pi h bar to the power 3/2. And for example, as an exercise, you might show the following. So if we apply the position operator on the state psi of RT, here I could also indicate it with a hat to denote the fact that we apply the position operator to psi of RT, and we can use the Fourier transform representation of this function that I simply wrote in here. So this would be equal to integral r, here we have just the vector r, e to the I over h bar p dot r, and then we divide by 2 pi h bar to the power of 3/2 phi of pt d3p. You can show, now I will skip some steps, you can show it as an exercise, in particular by rewriting this r as h bar over I derivative, the gradient with respect to the momentum. So this would be a vector characterized by the three components d over dp1, d over dp2, d over dp3. You can check that if you apply this derivative to this complex exponential, and by the way, when you write it as a derivative, you have to put the parentheses here because the derivative acts only on this complex exponential, not on phi, by assumption. So you simply rewrite the same integral by using the fact that you can replace r with this operator, and you can check that if you apply the derivative to the complex exponential, only to the complex exponential, you get back the expression there. Of course, you need to multiply by h bar over I to cancel this factor, right? And then you integrate by parts. So once you integrate by parts, the operator will act on phi, assuming that the boundary, at the boundary, the boundary term will give 0, because you also get a boundary term when you integrate by parts, but you assume that this function decays quite fast at the boundary and you can neglect it. And so after you integrate by parts, you can show that the operator r can be replaced by minus h bar over I d over dp. So it is something very similar to what you do in the coordinate domain, in the position domain in particular, because in that case you replace momentum, the momentum operator, by something similar, minus I h bar. So you see that this factor I appears here. It's like this one but with a different sign, basically, because you can also write it as, for example, plus h bar over I, since if you multiply by I, the numerator and the denominator, here in the denominator you get a minus, so it's as if you can write it as minus I h bar or plus h bar over I, and then here you have the gradient but with respect to the position, not the momentum. So you have something like this, and both in the position domain and in the momentum domain, the usual commutation relation between position and momentum is satisfied. And in particular, this commutation relation, so this is a commutator between the variable x and momentum p, this commutation relation gives rise to I h bar. So it's related to the Heisenberg uncertainty principle, and I think that that's it for this video.